In this video, we dive into propositional logic proper by looking at the propositional connectives. You'll know what all that is in a moment. Propositional logic is a logical calculus that takes as its basic unit the proposition. So that's not going to be very helpful until we flesh out what a proposition is and what it would mean for a logical calculus to take a proposition as its basic unit. So look at the following four sentences A through D and ask yourself which of them are propositions. Notice they're all sentences, but there's some difference between them. A is a question. It's asking whether it's raining today. It's not asserting a fact of the matter. Same thing with B. It's not asserting anything. It's simply commanding you to do something. Get away from here. By contrast, C and D both assert a state of affairs. They could be either true or false. If you say it is raining today, you're either correct or incorrect. You're stating how things are. Same thing with D. You are stating that things are such that it would be wise to get away from here. So C and D are propositions. Notice only C and D have a truth value. That is, only C and D can be true or false. So we're dealing with propositions like C and D that assert some kind of content. What we want to do is build up a machinery for understanding the logical structure of propositions. So take a minute to look at the list of words on your screen: tree, Susie, the Lakers, Socrates, and so on and so forth. Now compare those kinds of words to the words over here: and, or, if, then, and not. In logic, we single out the words on the right-hand side as playing a very specific role in sentences. Notice each of these words is meaningful on its own. Tree designates the set of all trees. The Lakers designates the set of all basketball players who are on that team. Socrates designates Socrates. We could put these words together into sentences, but they also have a meaning on their own. Contrast that with the meaning of the words on the right. These don't mean anything unless they've been put together with other sentences. As a matter of fact, the meaning of these words just depends on the meaning of the sentences that they're being used to operate upon. Here's an example. Suppose we have these two propositions, A and B. LeBron is on the Lakers. Apple makes the iPhone. And then we can put those two together using the word and. LeBron is on the Lakers and Apple makes the iPhone. Notice the truth value of proposition A is independent of the truth value of the proposition B. However, the truth value of proposition C is precisely a function of the truth value of A and B. Logicians have noticed that as a general matter, these words can be understood as propositional functions. That is, input other propositions and you output a new proposition with more logical structure. Compare propositions 1 and 2 and notice that 2 has more logical structure than 1. That is to say, the truth value of 2 depends on the truth value of it is raining today on the one hand, and then I forgot to bring my umbrella on the other hand. So we say that words like and introduce additional logical structure. In order to capture the idea that these logical words introduce logical structure, we're going to give them special symbols depicted over here on the right. So when we say that propositional logic takes the proposition as its basic unit of analysis, what we're saying is take a look at proposition 1. We're going to say this has no logical structure. So we're going to represent a proposition with none of those special logical terms in it as a basic unit with no further internal differentiation. As opposed to proposition 2, we're going to represent this proposition as a conjunction of this unstructured proposition with this unstructured proposition, so that as a whole, proposition 2 has some complex structure indicated by this word and. Now let's introduce each of these symbols more formally. The first symbol is conjunction. This is when we want to take two propositions P and Q and put them together to form a new proposition P and Q. So to define the conjunction operator, what we want to do is think, under what conditions is the sentence P and Q true? So take, for example, Alice attends the meeting and Bill attends the meeting. Well, that's true just in case both of these sentences are true. Otherwise, it's false. We can represent that information with what's called a truth table. So notice, a truth table defines the conditions in which a logically complex sentence is going to be true. Now, we're combining two propositions, P and Q. So what matters about whether P and Q is true is how things stand with P on the one hand, then Q on the other hand. If P is true, that is, if Alice attends the meeting, and if Q is true, that is, Bob attends the meeting, then P and Q will come out true. And that's the only case in which it comes out true. Notice, if Bill does not attend the meeting, if Q is false, well then P and Q must be false as well. Similarly, when P is false, we get false for P and Q. The next bit of logical vocabulary is the word or. We're going to use this V or wedge symbol to stand for or. So anytime we have proposition P and proposition Q, we can put them together with the disjunction operator, P or Q, to get a new proposition. Then we want to ask ourselves, in what circumstances is a sentence P or Q true? As a matter of fact, there's an issue involved in defining disjunction that requires pausing upon. Suppose Alice and Bill are talking and they say, "What's Jim up to tonight?" Bill says, "He told me that he's either going to the game or watching a movie." Now suppose Jim ends up doing both. Is Bill's statement true or false? He said he's either going to do one or the other. Well, it depends on if we're reading the disjunction in the inclusive or the exclusive sense. An exclusive disjunction is when, by saying either or, you're saying it's one or the other, but it's not going to be both. On an exclusive reading of disjunction, if Jim does both, then the proposition is false. That is, we can think of Bill as saying he's either going to go to the game or he's going to watch a movie, but he's not going to do both. We can also read the word or in the inclusive sense, that is to say, it's going to be one or the other, but it could be both. On this reading of Bill's comment, if Jim goes to the movie and watches the game, then the proposition he either went to the game or watched the movie is true. In symbolic logic, we're going to use the inclusive disjunction. That gives us the following truth table. So we have P, Alice attends the meeting. Q, Bill attends the meeting. Either Alice attends the meeting or Bill attends the meeting. Notice that on our inclusive read of the disjunction is only false in one case. That is, when both P and Q are false. So if I say Alice is going to attend the meeting or Bill is going to attend the meeting, what I've said is only false if neither of them ends up attending the meeting. If one or the other ends up attending the meeting, then what I said is still true. And if both of them attend the meeting, then what I said is true, since we're using the inclusive reading of disjunction. Again, these tables give you a view of how we're defining these logical constants in terms of the simpler constituents that make them up. This is like a function. We can input P and Q, and we get an output of truth value. The next logical connective is the conditional. This is when we put propositions together using the words if and then. If P, then Q. The symbol we're going to use is this arrow. Other logic texts commonly use this horseshoe. You'll see both in the courses of your study. So, for example, we have if Alice attends the meeting, then Bill attends the meeting. Under what conditions is P arrows Q true? This is a little bit unintuitive, so we're going to be using a very highly idealized version of the conditional. We'll talk about some philosophical problems with that in a moment. Here's the truth table. Notice the conditional is only false in one case, that is, when it takes you from a truth to a falsity. That's the only time we're going to define the truth conditional as false. Otherwise, it's going to be true. This might sound very odd to you, but what you need to do is simply memorize this truth table, and the reason we're doing things this way will emerge as you practice. Finally, there's one last bit of logically privileged vocabulary for which we need a logical constant, and that's the negation. The negation is a little different than the connectives because it's going to take only one proposition as input and output a new proposition. You take in P and you get not P. So for example, Alice attends the meeting. Alice does not attend the meeting when we add the negation. And as you might expect, the negation's truth table is fairly straightforward. The negation symbol simply flips the truth value of the input sentence. It's important to simply memorize the truth tables. You don't want to think about them, but use them as an algorithm for calculating the truth values of logically complex sentences based on their input truth value. This week, you need to memorize the truth tables for these connectives. This will just be something that we assume throughout the remainder of the course. It's easy to memorize the first two rows of all the truth tables except negation. They're exactly the same. On the first column under P, you'll put true, true, false, false. On the second column under Q, you alternate true, false, true, false. Then just memorize the third column for each of the individual connectors. Ultimately, we want to be able to use these logical constants to translate from natural language into propositional logic in such a way that we preserve the logical structure of the natural language sentence. Notice that all we're trying to do here is preserve the logical structure. So a lot of the natural language characteristics are going to be lost in translation. Here's an example. It was a dream, all a dream, that ends in nothing and leaves the sleeper where he lay down, but I wish you to know that you inspired it. A beautiful bit of natural language, and our translation into propositional logic, when all we care about is preserving the logical structure, just looks like this: P and Q and R. It was all a dream that ends in nothing and leaves the sleeper where he lay down, but I wish you to know that you inspired it. So we've captured the logical structure, that is, the way the truth of the whole depends on the truth of the parts, but we've lost all of that beautiful connotation and metaphor. Let's go through another example. I'm trying to translate this from English into my symbolic language. So the first thing I need to do is identify all of the atomic propositions. What is an atomic proposition? Well, it's the basic units. It's the propositions that have none of the logical vocabulary. For each of these atomic propositions, I'm going to assign a propositional variable, and then I'm going to use my logical vocabulary to put together those propositions in the correct way. First, I see my first atomic proposition is it is raining, so I'm going to assign a propositional letter to that. Let's say P. My next proposition is it is not raining. Now notice that's going to be built out of the same proposition as it is raining. So we don't actually have a new atomic proposition there. So the next new atomic proposition is I am staying inside. So let's assign that a new propositional letter. Q equals I am staying inside. And then we've got it's raining again, so that's already assigned a letter. And we've got a new one here, I'm going to the beach. So let's assign that R equals I'm going to the beach. Now that I've got my atomic propositions, I can start introducing my logical vocabulary. So notice I've got it's raining, so I'm just going to write my P here. It is raining. That's connected to another proposition with our logical vocabulary or, and that translates into my wedge symbol there. Now notice when it comes to it is not raining, we could assign, say, U to it is not raining. But we've lost some crucial logical structure if we've done that, because the proposition it's not raining depends for its truth on a simpler proposition, that is, it is raining. So it is not raining is true just in case it is raining is false. So we want to capture that, and it's the wrong way to go about it to assign it its own proposition letter. We don't want to take that approach. Rather, we want to use our negation symbol on P. So it is not raining. Here we have, it's not the case that it is raining, and that finishes our first sentence there. Now we've got it's raining again, so we're going to use that very same letter P to represent that. And that's being embedded in an if-then statement. So we pull out our arrow, which translates if-then. Now we've got I am staying inside, so we have assigned the letter Q to that. So we're good on that second sentence. And in the third sentence, we've got another arrow statement, and it's going to connect P and R.